All right, welcome to the Explainer. You know that feeling when a new technology just changes everything? Kind of like how GPT changed the game for language and code? Well, we might be standing on the edge of that exact same moment, but this time for robotics. We're talking about teaching robots to actually understand the physical world.
So to really get why this is such a game changer, you gotta look back a bit. Think about AI for language, say back in 2005. It was rough. It was all about manually coding every single grammar rule by hand. And sure, it kind of worked, but it was so fragile. One weird sentence and the whole thing would just break. It just didn't scale. Well, guess what? That's pretty much where robotics is right now. We're stuck in that same place, hand-coding physics into simulations, and it is holding us back big time. And that leads us right to the absolute core of the problem, what everyone's calling the robotics data bottleneck. Think about it. For a robot to work in the real world, it has to deal with chaos, right? A messy kitchen, a warehouse where things aren't perfectly stacked. To learn how to handle that, it needs a ton of data, an absolute mountain of it. And right now, getting that data is either super slow and expensive, or it comes from these really rigid simulations that just don't capture reality. And when I say expensive, I mean really expensive. We're talking about the industry spending a projected $3 billion just on trying to get enough data. That's an insane amount of money to pour into a method that, at its core, just isn't scaling up.
Okay, but here's where things get really exciting. There's a new approach called a world model, and it promises to do for robotics what large language models did for text. It completely flips the script on how we teach a robot to learn. So what in the world is a world model? Let's break it down. Think of it like an AI that develops physical common sense by just watching videos. Seriously, it just binges millions of hours of online videos, people cooking, things falling, cats knocking stuff off shelves, and from all that, it builds its own internal map of how physics works. It's not learning equations from a textbook. It learns gravity by seeing a million things fall.
And what's really cool is how this approach splits learning into two separate jobs. First, you have world knowledge. This is the general physics of everything, how stuff moves, falls, squishes. And the AI can learn all of that from that endless sea of internet videos. Then you have action knowledge, which is just about its own body. How do I move my arm? And it turns out that second part needs way less specific data.
So the big unlock here is pretty simple, right? You let the robot learn the hard part, how the world works, from this giant free library of video that already exists. That means you can slash the amount of expensive robot-specific data you need. It's about building this huge foundation of general knowledge first. So how does this actually play out? Well, this might be the wildest part. It allows the robot to train inside its own imagination. It can run through scenarios, make mistakes, and learn from them millions of times over without breaking a single physical object.
The whole process is this beautiful, simple, three-step loop. Step 1, learn. The AI watches videos to get that physical intuition. Step 2, imagine. It runs countless what-if scenarios inside its own head. And step 3, refine. It takes what it learned in its imagination and uses just a little bit of real-world data to calibrate it all to its actual physical body.
And that's the key. Being able to fail hundreds of thousands of times a second in a simulated world. That changes everything. It's no longer a hardware problem, limited by how many physical robots you can build and run. It becomes a compute problem. And we've all seen this movie before, right? When a problem becomes about compute, you can just throw more power at it and progress just explodes.
And look, this isn't some far-off sci-fi dream. This stuff is happening right now. We're already seeing some jaw-dropping results from these models. It's a total paradigm shift, and it's already working.
Yep, all the big names are jumping in. You've got NVIDIA, Google DeepMind, Meta. They're all building these massive models, scaling them up into the billions of parameters. It is an all-out race to build the best physical AI. I mean, just look at this number, 80%. That's the success rate Meta's model got on tasks it had never seen before. That's what we call zero-shot performance. It's like asking you to perform a complex task you've never been trained for, and you just nail it. It is the holy grail for general AI.
And here's the kicker. How much specific robot data did it need to get that 80% success rate? Just 62 hours. 62. Compare that to the thousands of hours older methods needed to get anywhere close. The jump in efficiency here is just mind-blowing.
Okay, so things are looking pretty amazing. But let's be real, we're not there yet. To give you the full picture, we got to talk about the big hurdles that are still standing between these cool lab demos and a robot that's actually, folding your laundry.
It really boils down to three big things. First, there's a blind layer. Video can't teach a robot what something feels like, right? The weight, the friction, the force. Second, they're not quite consistent or fast enough for real-time reactions just yet. And third, man, the cost. The price tag to train and run these things is just enormous.
Yeah, let's just double-click on that cost thing for a second. We're hearing estimates of around $100 per hour just to run one robot on a model like this. Think about that. You're not going to pay $100 an hour to have a robot fold your t-shirts. It's just not sustainable for, well, pretty much anyone.
So, that's really the state of play. The understanding part of the puzzle, we've largely cracked it, which is incredible. Now the race is on to solve the other two big pieces. The sensing piece, giving robots a sense of touch, and the serving piece, making it cheap enough for everyone to actually use.
And that really leaves us with one big final question. The basic blueprint, the fundamental code for a robot that can think and act in the physical world, it's being written right now. It's happening. So the question isn't if these robots are coming to our world. The only question left is when.